Couple of applications here, right? Mirages. We heavily look at mirages for refraction of light. So based on different air densities, right, we actually get a different amount of refraction based on the air temperature, right? As the air temperature increases, it lowers the index of refraction, right? Which means that light speeds up so it bends away from normal. So when you see a mirage, it's always that upside down appearance. And that's because the light that is going from, in this picture, the trees, that light is heading towards the ground, but as that air warms up, it actually bends it back up towards the observer. So that's where we get that upside down look from, right? So we get direct light to show the true image. The refracted light is going to head down towards the ground, but it doesn't make it to the ground because that air temperature changes, which changes the index of refraction, which lets that light bend back towards the observer. Another application of refraction is dispersion, right? And dispersion is how we separate light into its individual components, right? So we're taking light of multiple wavelengths and then we're going to separate it into its individual pieces. And the refraction ends up being dependent on our wavelength, right? So some waves are going to refract more than others. The shorter the wavelength is, so the higher energy it has, we're going to see that is going to refract more, right? So short wavelengths have higher energies. They're going to bend more. Longer wavelengths with lower energy are going to bend less. That's why when we look at our visible spectrum here, and when you look at a rainbow, you have red on the outside, violet on the inside. Think about the electromagnetic spectrum here. The violet has the highest energy, the shortest wavelength of the visible spectrum. Red has the longest wavelength, the lowest energy, so it bends less. When we take a look at a prism here, so our same glass prism, so here we have just white light coming in at an angle. It makes contact and that light is going to disperse, right? That light disperses. That means it spreads out into its individual components. So as it spreads out, what we notice is that the red doesn't bend a whole lot. The violet bends the most, and then your Roy-G Biv, right, obeys in its proper order that we see. Then that light leaves again, right? So now it leaves the prism back into air where it now speeds up. And as it speeds up, we bend away from normal where we get even more separation of those colors. So as this light disperses through the prism, we get the light to slow down in the prism, so the light bends towards normal. Then as it leaves the prism, it bends away from normal. But each time, the violet is going to respond most, the red is going to respond least. And here's just another look at it where you can see the angles and what's all happening here, right? So we have the normals drawn on each side. And as that light bends, right, we get less bend out of the violet, or we get more bend out of the violet in both situations, right? We're just bending towards normal as it enters and bending away from normal as it leaves. But again, just take a look at this one here, right? Less refraction for red, a little bit more for orange, a little more for yellow, a little more for green, all the way down to violet. Now, rainbows is our application of dispersion. So when light enters a raindrop, it's going to behave very similar to a prism, except we're going to have total internal reflection. So the light enters every single droplet of water. That light then disperses, right? We undergo refraction. That light spreads itself out, and then it gets to the back of the droplet of water. When it gets to the back of the droplet of water, because it's trying to go from water to air, the light would speed up as it does so, but the way that the light hits the back of the raindrop is it is greater than that critical angle, so we see total internal reflection. So the light reflects back towards the front of the raindrop, where now it's able to hit that droplet in the front at an angle where it can escape, so we see that light bend and it refracts again. So we get two refractions and an internal reflection in the middle here. And what's interesting, and if you notice, as that light leaves the droplet, the violet or the blues are going to be at the top and the reds and the oranges are actually going to be at the bottom, which is an interesting phenomenon considering how we see rainbows. Reds on top, the blues and violets are at the bottom. Well, the rationale behind that is how that light then leaves. So the blues and the violets leave at 40 degrees, the red leaves at 42 degrees, which as they then travel, so they spread out, so you'd be going, oh, well, the violet should be at the top. The problem is when that light leaves, the violet rays that are high enough up in the atmosphere pass over the top of you. You never see them, right? They don't actually get to your eye. They pass beyond and continue traveling. So the highest droplets that we see are red because those are the first rays of light that are able to get to us based on the angle. So then the lower droplets are going to be violet because now if you notice the way that that light travels, when it's lower, it's a more direct path to our eyes. The red doesn't get to us. It hits before us. It's hitting our feet. It doesn't actually reach our eye because it's too low for us to observe. Right, so that's where we look at this here. And just an interesting thought on rainbows. Right, where's the sun always located? It's always located behind you because of that total internal reflection that occurs within the raindrop. And the diagram here in the bottom right emphasizes that very, very well. That sunlight has to come in and then be reflected back towards you via that total internal reflection.